Here we start addressing how different building standards improve the energy efficiency with regards to heating and cooling, that is, reducing the need of the building for heating and cooling. We talked about these two ASHRAE standards that define the boundaries of the energy balance, as well as the definition of what a zero net energy and what a zero net carbon buildings are. And now we start looking at applying these building standards to different projects to see how more or less efficient they become. So for heat and cooling demand, this is what is calculated in PHPP. It basically addresses the net need for heating and cooling that the building has, regardless of the type of heating and cooling system. It's just the efficiency of the building envelope. That is the amount of insulation, the air tightness of the building envelope, the quality of windows and doors, the passive solar gains through windows and doors, things like that. So in the diagram of these energy boundaries on the left side, you see we highlighted in orange what is the fabric or the building envelope, the building thermal envelope. Now, looking at the different standards, we calculated each project, 50 of them, for each variation of the different building standards. It's about a dozen. And we looked at the heating and cooling demand calculated in PHPP. So these numbers are driven by the climate, by the geometry of the building, the form factor, how complex the shape is or how simple the shape is, the orientation, the passive solar gains, and the amount of insulation and air leakage that we can expect by buildings built and designed depending on each building standard that we have. And you see, in general, looking at apples to apples, the left side table, the orange one, has much more intense colors, meaning that there's higher demand for heating than there is for cooling. That is for all projects, even for projects located in warm climates. Now, this is just what the building needs for to remain comfortable. It's not addressing yet a mechanical system. Talking about, so in fact, this picture here is from a passive house project being built in Colorado, and it's empty. It's just the hole is just the building envelope. Now we start talking about the heat pump. One of the premises of the study is that all projects and all building standards were assumed to be all electric and to have a heat pump to provide both heating and cooling. And some building standards do have requirements for that heat pump in terms of minimum heating performance and minimum cooling performance, and others don't. So we put together this kind of table listing what kind of performance we assumed in terms of modeling. Basic heat pump is what we assign to those building standards that don't have requirements for performance, including the International Energy Conservation Code, IECC, including PHI Passive House and Low Energy Building, because that has some limits in terms of total primary energy or total source energy, but they don't mandate which type of heat pump that you need to use, as long as you meet that requirement. It's very performance-based. Then California 2024, EnergyStar, Zero Energy Ready Homes, and PHIUS Prescriptive all have specific requirements for the minimum required performance for the heat pump in terms of cooling efficiency, SEER, and heating efficiency, HSPF. And in general, you can see that the SEER numbers are greater than the HSPF numbers, meaning that the same heat pump performs better in producing cooling than it does in producing heating. We talked in one of the earliest videos, we talked about the priorities between heating and cooling. And this is one of the reasons why we typically recommend prioritizing heating efficiency even in hot climates, because heat pumps are better at producing cooling than they are at producing heating. Then next, so once we apply the heat pumps to the energy, the heating and cooling demand that we saw in the previous slide, then we have the site energy for heating and cooling. And when we combine the two of them, we start seeing how the different building standards improve the overall energy efficiency of the buildings in that they reduce the need for heating and cooling. This is summarized in this table. And to give you a better idea, we see this bubble chart. On the x-axis at the bottom, we have the projects that we modeled, number 1 to 15. You see the bubbles that are at 0 is because the standard did not have any requirements for that climate, so we eliminated those. And then you see in gray, you see the 2021 Energy Code. You see in orange, you see PHI Passive House and Low Energy Building. In blue and light blue, you see PHIUS Core and PHIUS Core 2018, as well as PHIUS Core Prescriptive. And in green, you see Pretty Good House. Now, this is important to see, to benchmark against a baseline. And the baseline for the whole study was the 2018 Energy Code, so the 2018 IECC. Now, this is the reduction, and more importantly, when we start talking about, we're going to see this the result from this table in a more attractive and understandable form of graph. When we start looking at performance by climate, this is what it looks like for warm climates. So in general, in warm climate zone 2 and 3, for the projects that we modeled, the 2021 IECC would result in a reduction of heating and cooling by 16% compared to the 2018. The 2024 IECC actually performs a little bit worse, with 14% reduction. And all the way to the other side of the spectrum, we have the passive standard that performed between 40 and 50% reduction of heating and cooling in warm climate zones compared to the 2018 IECC. Coming to mild climate zones, the spread goes between 9% reduction for the 2024 IECC, which is the one that performs less well, all the way to 73% for PHI Passive House, with the other passive standards around 50 to 60%. And when it comes to cold climate zones, climate zone 6 and 7, you see that the least performing is the 2021 IECC, and the most performing one is PHI Passive House with 86% reduction for heating and cooling compared to the 2018 IECC, with PHIUS and Low Energy Building around 70 to 75. Now, looking at the overall, remember that we have intentionally we have a split. A quarter of the projects are in warm climate, about half the projects are in mild climate zone, and the remaining quarter are in cold climate, and that of course impacts the overall results. Overall, in average, you can expect about 9% reduction compared to the 2018 Energy Code if you adopt the 2021 or the 2024 Energy Code. You see that the 2024 Energy Code, or the draft that we modeled, performs slightly worse than the 2021 Energy Code. Then the most performing is PHI Passive House with about 70% reduction of heating and cooling. And then the other passive standards are about between 50 and 55%, with the 2018 PHIUS being the second best performing, and the Low Energy Building being the third one. Benchmarking the performance against the 2018 IECC. So the graph on the left shows if I have 1 unit of energy loss for heating and cooling for the 2018 code, you see that PHI Passive House is at 0.29, so about 70% less, as we just saw. The other passive standard are about 0.4, 0.45. But more interestingly is that if you benchmark against the most efficient one, that is PHI Passive House, So if PHI Passive House is 1, then 2018 PHIUS and PHI Low Energy Building are about 1.6, so about 60% greater. PHIUS 2021 and 2021 Prescriptive are about 1.8 or about 1.9, so about twice as much. Pretty Good House, EnergyStar, and DOE Zero Energy Ready are about 3 to 4 times greater heating and cooling demand compared to PHI Passive House. And the IECC are about 4 to 5 times greater energy consumption for heating and cooling than PHI Passive House. So this is, I think, pretty easy to understand. It's PHI Passive House is the best performing with regards to the reduction of heating and cooling.